Calculus 2.7, Derivatives and Rates of Change. Our objective is to investigate the relationship between the secant and a tangent slope and apply the principle in rate of change problems, such as the motion of particle. Now, if you look back at the average rate of change right here, guys, right? It's some distance change in x or change in y this way. So there's some distance right there, right? And that's exactly what it is. M secant, the secant meaning a line that goes through a curve at two different points, right? Is basically change in y and change in x, right? So what we learned as a slope in our basic algebra class, that's the secant slope, right? We're trying to differentiate compared to other kinds of slopes. And that could be, let's say, for example, if this is, I don't know, x1, y1, and this is x2, y2, that distance right here, guys, and this is x1 and this is x2, this change in x is basically x2 minus x1. This change in y, which is y2 is up here, y1 is here, it is y2 minus y1, right? And I just prefer to just think of it this way. Now, another way to think about this is the following. What if instead of saying x and y, and we just designate a slightly different letter, right? For purposes that which will become clear a little later on. What if you call this a, and let's call this x, and this will be f of a, and this is f of x, and that gap is x minus a, which is change in x, and this is f of x minus f of a, which is essentially the change of y. That fact hasn't changed, right? There's a reason why we want to do this, expressed in this way. Now, let's think what might happen if x approaches a this way, or the difference between them. We could call them, I don't know, change in x, or simply h. What happens when they go to 0? Okay. So what if the difference between these two becomes smaller and smaller and smaller? So for example, so instead of it being here, x, what if the x was, I don't know, a little closer right there, guys, right? Then maybe f of x will be here instead. So earlier I had something that looked like this, guys, right? So that would have been the secant slope, right? If I have one over here, it has to go through that point right there. So this one look more like that. Okay, I think that's more like it. So something that looks like this. That's interesting. So it's changing, right? All right, so I could only give you a static view of this. Okay, so we're gonna officially define this, guys, right? That tangent line to the curve y equals f of x, we're talking about this curve right here, guys, right? At point a f of a right here, is a line through P with the slope. In other words, when the x is approaching A, like that, right? That was a secant slope. If that got even tighter, instead of being that right there, guys, this thing, what if it was even closer, right? Let's bring it up this way, right? And then that point will be, I don't know, here. Oopsie. And then what that means is that f of x will be a little lower because it'll be, oopsie. Sorry about that. So it's going to go be like here somewhere, right? So that thing will drag down just a little bit. And the line that will be forming is like this, right? But that, if you look at it carefully, almost looks like it's a tangent point at this right here, doesn't it? It appears that that thing is getting closer and closer until it becomes a tangent mark. All right, so that wasn't such a great, I don't know, animation. Okay. Well, anyways, so in other words, as x approaches a, the gap between them gets smaller. This triangle gets smaller, and that secant slope we're claiming is becoming a tangent slope. I hope that's intuitive. And the only difference between this and this is that x minus a is being expressed as an h, as a single expression. And instead here, so what that literally means is that if we had a point over here, guys, right? And if the gap was h, then this would be what? A plus h. And then this right here, oopsie, what would have been here, right? That is the same thing as f of a plus h. So we replace f of x with f of a plus h, and f of a, which is here, with the original height. Oops, that should have been a, my bad. Sorry about that, that should have been a. Okay, so that's an alternate form to this. They're pretty much the same thing. Let me just show you a real quick graph. This, if you downloaded this through, what do you call that thing? PDF, this link is live. That's, I believe I've made that one if I'm not mistaken. So let's click on it, open a Safari. All right. Basically, I used the same picture. I mean, it's the same picture, right? And A was, let's make that a 0 because that's where it was, right? For us. Well, actually, was it a 0? No, never mind. It was actually maybe 0.6 right here. Right. And then that distance was a little far away, right? So if the gap between these two, h represents the gap between the x and the a, right? So if 1.37, in the green, you could clearly see that it's a secant. But as it gets closer and closer and closer like this, guys, look what happens to the black line. That black line represents the tangent line. Gets closer, closer, and closer. If you zoom in like this, you could tell there's a bit of a gap, but I gotta go really, really deep right here. And it's even hard to tell. I mean, it's, you know, and the gap is only like 0.001. Can you imagine if it was smaller than that, right? Anyways, you get my drift, right? So basically what it means is that by having a secant slope that we've always known, and if you make this gap small, then that secant slope becomes a tangent slope. And this is just an alternate way of writing it, okay? So this is like a bedrock fundamental idea on which the entire calculus is built, right? So here we go. Let's do a calculation. It's asking us to find the equation of the tangent line to the hyperbola y equal to 2 over x at a point 2, 1. Well, before we do that, let's check if it works, right? This is x, this is y. If I plug into the equation that was given to us, yep, it works. So 2, 1 satisfies the equation. Y is equal to 2 over x. Let's try to figure out what it's asking us. That is a hyperbola with a vertical stretch, right? It's a transformation of 1 over x. So it's going to look something like this. It's not a perfect picture, but it's close enough. 2, 1 will be here. So they're asking us to find this particular tangent line. Well, first of all, I know that this is what? X naught, Y naught. And I just need to find the slope, right? So the question is, what is my slope? All I know is my slope is negative, and it's not quite as steep as being -1. It's a little flatter. So -2/3, I have no idea. Okay, we'll figure that out. But according to this, we want to find tangent at 2. So we want to find the tangent, right? Tangent slope when x is 2. That's what we're looking for, right? So we could use the formula y minus y naught is equal to m times, is m tangent by the way, x minus x naught. We already have x naught, y naught. We just have to find the m tangent. And voila, here it is. So what I'm going to do is I'm going to do it this way first. Okay, let's do that, shall we? I'll take up all the space. So basically the m tangent is the limit as x approaches a. In this case, a is 2, right? Because that's where we want to find the slope right here, guys. That's where we want to find the slope. So that has to be the a. What that means is that we got f of x minus f of a over x minus 2. Well, f of x is what? It's defined to be 2 over x. F of a, if you plug it in, is 2 over 2. And that's x minus 2. Now we know that that's 1, right? To get rid of the denominator in the numerator, we just multiply by x over x like this, right? When you distribute the x throughout over here, that is going to become 2 minus x, and this becomes x minus 2 times x. Now, you could see that these two is essentially a minus b of b minus a, guys. It's just negative 1. So it cross cancels to negative 1. So what that means is that this thing is limit as x goes to 2, negative 1 over x. Okay. Now we have arrived at a point that we've been practicing for last week. To evaluate the limit, we could just simply substitute as long as it doesn't give you a undefined value, right? It's not giving you a weird value. Well, you could evaluate it, substitute it as long as this 2 is in this domain, and it is. And that, when you plug it in, is negative 2. So now we have tangent slope, which is, oopsie, negative half, and we got x naught, y naught is equal to 2 and 1. So using this formula here, guys, we know that it is y minus 1 is equal to negative half times x minus 2. Therefore, and we're done. So essentially it's telling you that at this point, my slope is negative half. Even though my picture is pretty rough, that looks reasonable, doesn't it? Okay. Now, I actually prefer to do it this way, right? So what I'm going to do is maybe I could just put in the next page. Sounds good? All right. And perhaps I should make this page. Oh, I don't know. How do I do this? Paper? Yes. Let's go with this one. No, this one. Okay, I like that one. All right, let's go with this one here, guys. Okay. So, see? Okay, it's not very responsive. There you go. All right. So now the question is, right? Y is equal to 2 over x, right? And they want to, given this, they want to find the equation of the tangent line at 2, 1. We've already plugged this into this equation. We know it works. The only thing that we really need, because we already know the x naught and the y naught, right? So we need to find, ask yourself this, what do we need? Well, I have a point, I just need a slope. So we just learned about m tangent, right? So what is m tangent? By definition, it is a limit as h goes to 0. That's the distance between 2 points, right? And f of a plus h minus f of a over h. A being the point that you want to go towards, right? Plug it in. So this, by the way, is just f of x is 2 over x, right? I'm just using that interchangeably, obviously. Now, when you do that, we end up with 2 over a plus h minus, what is that? 2 over a, right? Now, I suppose I could go over h, but I will have a complex fraction, right? So whatever we do, when you divide by a number, we multiply by its reciprocal. And I'm just going to put that in the front. So visually, it's easier to look at when you do that. Now that we have a difference of a, what do you call that thing? Fraction. We're going to have a common denominator, right? Right. And that's going to give you a times a plus h 2a minus twice the a plus h. When you expand that out, let's just do it one at a time. Okay, that's going to give you 2a minus 2a minus 2h, h times a plus h. They cancel. And what else cancels, guys, at this point? Well, h will cancel. So what that means is that we're going to have limit as h goes to 0 of negative 2a over a plus h. It is at this point that we could plug in for h. When you do that, it gives you negative 2 over a squared. So the equation for the m tangent is negative 2 over a squared. And you're sort of wondering why I gave so much space in between the two. Well, the a value in this case is what? 2. When you plug that in, that's negative half. Well, we know that y naught x naught is 2, 1. So given the formula for the linear equation, so that's y minus y naught, which in this case is 1, minus the slope, times x minus x naught. That is it, guys. Okay. There you go. All right, guys. So let's move on to this right here. Okay. So derivative f prime of x, I'm sorry. So this right here is pronounced prime. This little apostrophe right here, right? Is an instantaneous rate of change of y equal to f of x with respect to x when x is a. Well, I'm sorry. There's a typo here. That should have been f prime of a. Sorry about that. So basically what that's saying is this change in y over change in x, which is change in f of a over change in x. Okay. Or you could think of it as change in f of x and then replace the x with the a. Okay. And I think it's going to come up a little later, but this is called the prime notation, or some people call this the Newtonian notation. And then when you have like something like this, it's actually not really complete at this point. It's called Leibniz's notation, but we'll talk about that later, okay? So this is essentially what we talked about earlier, isn't it? The definition that we had. I actually prefer to go with that, okay? But the key thing is that this thing is called the derivative, right? We have a name for this now. It's derivative, not the limit of blah, 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 blah. All right. So the question is, now it's asking us to find the slope of the line, tangent line to the graph of the function square root of x at these points. We should check if this is actually valid. Let's do a mental check, shall we? So this is x, this is y. Plug in 1. Square root of 1 is 1. Check. Square root of 4, that's 2. Check. So it works. All right, so what does that mean? So if you have the square root of x, 1, 1, 1, 2, 3, 4, 2, the graph looks kind of like this. So you're looking for a tangent slope at this point and at this point. And so that's the first one. And that right there is the second one right there, guys, right? So we could tell that this slope is a little flatter. And this one, I don't know what it is right now, but it's definitely not 1, maybe half, a third, and this is even less, right? So it's good to have a sense of what it is if you can prior to doing this, okay? All right, guys, so let's get going. So when we do this over here, what do we do? Slope tangent, okay? So we're going to f prime of a is what? Limit as h goes to 0, f of a plus h minus f of a. I'm sorry, that should be a. I keep making the same mistake. Okay. Over h. And when you do that, I end up with Let's just use the letter A, shall we? We have limit as h goes to 0. So when you plug in a plus h into this one, what do you end up with? Exactly, a plus h, that's a over h. And from our past experience, we know that when you have expressions like this, conjugate seems to work nicely, right? So we're going to just go with that. So when you do that, what do we end up with? The first one is a plus h minus a over h times square root of a plus h plus root a. The a's cancel. And you know what? H is cross-cancelled, doesn't it? Right. So that is equal to limit as h goes to 0 of 1 over square root of a plus h plus square root of a. Now that you can plug in the h with direct substitution, because now it's safe to do so, isn't it? And that is 0 here, so that's basically 1 over 2 root a. I think we found a formula for this. I think we did. So in the case of 1, 1, x here represents the a, isn't it? So the slope, why don't I just move this out a little bit? Okay, so slope at that point is equal to 1 over 2 over square root of 1, which is half. And slope at 4, 2 is 1 over 2 square root of a, but a is 4, so that is 1/4. So what this showed us is that this slope is indeed half, and over here, my slope is 1/4. Even though it's a rough picture, that sounds about right, doesn't it? That's right. All right, guys. So we got 2 more questions, guys. This one, and I believe the next one. Okay. Why don't we save that for class? Okay. Because we should spend some time talking about this in person, so you could interrupt me and ask me questions in person. Now that we have that base, if we could work on this one. And if you have some questions on everything that I just did, like, I don't want to go too far into the lesson just on a video. Okay. All right, guys. I'll see you tomorrow morning, and we'll have a lot to talk about. Okay. Good night.